Hi, thanks everybody. I'm sure one or two people are still filtering in, so I'll get into the housekeeping, and then as you're all settling down, you can ignore the boring bits. My name's Ian Cooper. Hopefully you're here to learn about how we do Kafka in C#. If you're not, there's still time to run for the exits and get a different talk instead. Those are my socials. It's iCooper on HackyDome or Twitter. Actually, I weirdly in a current world post tech stuff to LinkedIn. Who'd have thought that? This is me. It just says I'm old. I've been doing messaging for quite a while. We actively use Kafka at my current place of employment, which you call Menulog. For anyone who, I guess you're all .NET developers, otherwise probably you're lost and confused and in the wrong room. But I work on a messaging framework for .NET called Brighter and other people. And we are an alternative to things like mass transit and then service bus. And we support Kafka, and we do that natively. It's not a kind of addition to our platform like it is in mass transit. For this talk, you can get the sample code on GitHub. You can get Brighter on GitHub. This presentation, well, actually a slightly earlier form of this, is in my GitHub as well. It's in a PDF. I will upload this current version later on today. It's in a PDF rather than a PowerPoint because it's too big with the graphics. So GitHub won't accept the actual PowerPoint file. All right, what we're going to talk about. So we'll talk about Kafka. We'll just introduce you to what it is, where it comes from, how it works. We'll talk a tiny bit about how you manage a Kafka that you have running. And then we'll get into Kafka and C#, and we'll show you an example of consuming and producing a message using Kafka. Then we'll dig a little deeper. We'll talk a little bit about how Kafka works under the hood that may help you. And then we'll talk a little bit about making our producers reliable and our consumers reliable. And we'll finish, we're going to be tight for time, but we'll try and finish with this conversation about how we do serializers and deserializers in the schema registry, right? That should give you everything you'll need to kind of begin to grok to do Kafka in .NET, right? You have to probably go away afterwards and dig deeper into some of the topics. All right, what is Kafka? So Kafka was built in about 2011. Jay Krebs, Neva Nakadi, and June Rao, they all worked at LinkedIn. And they worked in the data engineering team at LinkedIn, and they found themselves in a situation where they had a lot of sources of data that they wanted to collate together effectively in a data warehouse. And they had a lot of disparate ways of doing that at LinkedIn, and they felt, hey, there must be a way we can kind of standardize this process. And the result of that was Kafka. So looking at that diagram behind you, behind me rather, you can see you have a producer. And the producer is effectively writing a record. When it writes that record, it writes it to an append-only log. What we mean by that is essentially it can do it as a file, on which a writer can only write at the end. They can only append new items. They can't overwrite things at some section in the log. Makes it very fast. Writers read from the other end of the log effectively until they have caught up, essentially with the writer. So the readers read from 1 up here up to about 15, and producers writing at 15, 16, 17. Because we have this log, we create an asynchronous conversation. And by that we mean both parties don't need to be present at the same time. The producer can be writing records and information to the log. The consumer can be being rebooted, down for maintenance, releasing a new version. And when it spins up, it just goes and effectively starts reading the log from the last place that it read to. And because both parties don't need to be present, we call it an asynchronous conversation, or more normally, messaging. Right? So this is a way of doing messaging. It differs from queue-based systems like RabbitMQ, SQS, etc., which are a queue, not a stream. It has some different characteristics. Okay. So my producer writes a record, and a record has a value and a key, right? So the value is whatever you want it to be. A key is also pretty much whatever you want it to be, but you're essentially tending to place the key on whatever it is you're observing. So the thing upstream, a restaurant, a customer, what's the key value for that? So it uses TCP/IP, it connects to the broker, and it writes it to what we call a topic. So a topic's just a name for one of these append-only logs. It's a way of us addressing it by a name rather than some more technical, URI, etc. So we can both refer to the name. So this name could be restaurants, customers, and anything we wanted to both observe. So the topic is this append-only log. What a consumer then does is it reads from the same topic. And as it reads an item, it is non-destructive. So unlike a queue-based system like RabbitMQ or SQS, where when you read an item, you effectively delete it, we don't. We leave it in that log. Anybody else can come along and read that log now as well. So how do we know how far we've read? What we do is we maintain an index saying, well, what items have we read in that log? And we store that in what's at a topic that's called consumer offsets. So offset just means what is our index into that particular log, right? The offset from the beginning of the log. How far have we read up to now? If we get another consumer, that consumer will essentially track its own set of offsets in the log. Another consumer, new set of offsets in the log. That means, unlike, say, a queuing system that you might have used in the past, adding new consumers doesn't make us go faster. Right? They'll all just start reading at the beginning and reading their way through the log, record by record through the log. So what happens if we are getting people arriving in that log faster than we can read it with a single consumer? So Kafka has the notion of partitions, which you can see on this side, on the right-hand side of the screen. Right? So the idea is we slice up our topic into a number of partitions. Each partition is essentially its own little mini append-only log. The producer, when it gets one of these records on the left-hand side, what it's going to say to itself is, okay, I'm going to take that key and I'm going to use that key to determine which partition to write to. Now, you could be random. If you're random, it's probably not what you don't have a great use case for Kafka. But you more normally, for any given observable, you want to see records for it in sequence or in the order they were produced. So you want them to go to the same partition. So you want key 1, 2, 3 to go to partition 0, key 1, 2, 4 to go to partition 1, maybe key 1, 2, 5 goes to partition 0, maybe key 1, 2, 6 goes to partition 2, and every single time something with that key goes to the same partition. And that idea is what's called consistent hashing. So we hash the key value and make sure it always appears on the same partition. My consumers read not just actually a topic, but a partition on the topic. So my consumer is going to walk through that given partition, recording its offsets on the partition. So if I have, in this situation, 2 consumers and 3 partitions, what would happen is Kafka would say, okay, one of you is going to have one partition, maybe the top one, right? You have one partition, partition 0. It starts at offset 0, 1, 2, 3, works its way through. The other consumer is going to get partition 1 and 2, and it works its way reading through those, marking the offsets it's reaching in each partition. So it's just offset 0, 1, 2, 3 in partition 1, 0, 1, 2, 3 in partition 2. We could have 3 consumers here, 1 for each partition. We could have 4 consumers, but one of those consumers would be doing nothing, because essentially you could only have a maximum of 1 consumer reading a partition at a time. That ensures the items will be read in sequence. Okay, so we will preserve the sequencing for a given key value by writing things in order to that partition. So I can't have multiple consumers on the same partition. So if I've got a spare one, it does nothing. Why might I have a spare one? Generally, for redundancy, one of my consumers crashes, that one will immediately be reallocated, one of the partitions that now is missing. Okay. Now, if I have multiple applications, what I want to be able to do is say, okay, you have a group of readers which are all essentially going to agree that you are reading through the partitions on a topic, and you're moving your offsets along in sequence. But this other app may want to start from 0 and reading its own set of partitions. So what we do is we give our groups of consumers a group ID. And any consumer in that group ID will use the offsets for the partitions we have written for that group ID. A new group ID, new set of offsets into that for those partitions, right? All right, so let's try and recap all of that, because it's quite a lot to take in early on in the talk. Over on the left-hand side, I have a producer. I want to write records. Record is really a Kafka name for a message. You'll see message used as well. Kafka's documentation changes over time. People use the term interchangeably. So I want to write a record, or I want to send a message. So that message consists of a value and a key. The value is the data I want to exchange with you. A key is a way of identifying the observable it's coming from, right? And typically, I want to write them so that all of the changes to a given observable, 1, 2, 3, 1, 2, 4, 1, 2, 5, are in sequence. So I talk to my Kafka broker, and I say I want to write to this topic. And essentially what I do is use an algorithm, usually consistent hashing, to figure out which partition I'm writing to. So 1, 2, 3 goes to 0, 1, 2, 4 goes to 1, and let's say in this instance 1, 2, 5 goes to 2, right? The consumers for a given group parcel out those partitions amongst themselves. So group alpha here has got partition, one of the consumers has got partition 0, other one's got 1 and 2, and they will read through them in sequence. And as they read records from basically that topic, they will write the offsets for the records they have written to a special Kafka topic, so that if they crash, then essentially the thing that comes up can say, where were we? And resume reading from that point. Okay. Or if I need to scale out the number of consumers because maybe I only had 1 reading because we were in a quiet period, and now I want to go up to 3 because we're in a busy period, what happens is partitions can get reallocated. And so the new consumer coming in saying, I can do some work now, needs to know the last point we reach. So it will read it from that consumer offsets table. Okay. And I can have multiple groups, all of which maintain their own offsets for each partition. And that is how Kafka works, right? That's the bit you need to grok. And yeah, it's very different to a queue-based system, which is when you read is destructive and takes items off the queue so nobody else can read them. It is very good, particularly for pub-sub style scenarios, where essentially you want to say, I want to broadcast this and I want lots of people to read it, because it tends to basically only have the 1 copy and it's very fast, right? It's less good for I want to hand you a task and no one else should do it. All right, we're done. No, okay. Right, what about managing Kafka? Generally, you can use both CLI tools and UIs to investigate stuff. Normally, when you're effectively got a production system, you'll be using CLI tools a lot. So Kafka comes with a set of CLI tools. You can see that on the left-hand side. It's basically in a bin file wherever you install Kafka. There's a whole range of little utilities like create or delete topics. You get little tools to actually create on-the-fly producers and consumers, to manage offsets, and many more, right? If you prefer to work with the command line to just investigate Kafka, or you want to do some very simple local kind of like tools to look around what's in that topic, can I get stuff out? There's a great tool called KCat. So KCat essentially used to be called Kafka Cat, is described as a generic non-JVM producer and consumer. And what that lets you do is read and write from given topics from the command line. Very useful, particularly if you use it alongside tools like JQ, if you have kind of JSON payloads to kind of like play with what's actually happening in your environment. Kafka also has a range of UIs. This one up here is Kafka UI. You'll see Kafka UI in a few demos later, but there's AKHQ, Kafka Drop, Lenses, and CMAC are all basically open source ones, and there are paid ones from Confluent and Conductor. So a whole range of UIs, and they'll let you see topics, investigate messages. So if you'd rather work with a UI, you're still supported. All right, let's get into the meat of it you probably care about is if I'm a C# developer, what do I do? So we're going to look at this we're going to build an app, and we're going to use an app to do some transmogrification. Anyone in the room know who Calvin and Hobbes are? Vanishing in smaller numbers and numbers of people. I feel old whenever I ask. Calvin and Hobbes is an old newspaper comic strip cartoon. I used to like it. And Calvin, who's a small child, and his cuddly tiger, Hobbes, who is kind of like a figure in his imagination, have lots of adventures. One of them is Calvin has a cardboard box which has transmogrifier written on it with a little dial, and Calvin can transmogrify himself into things like eels, worms, baboons, and tigers. So rather than hello world, we're going to build a transmogrifier. We're going to essentially have a producer application that says, hey, what do you want to be transformed into? Get some settings of us, sends it via Kafka to the transmogrifier, which will transform Calvin and change him into something else. Right. I got bored with hello world. All right. So how do we produce a message in Kafka? So this dispatch application, we'll see all the code later. I just want to walk through bits of the code in the slides. You can see here, essentially, we've got a private read-only producer. We get that from but generally most of the libraries from .NET here are Confluent .NET libraries. We have a producer builder, and we say to it, build us a producer. So the producer is the thing we're going to use to send the record. And we pass it some config. Okay. And the config that we want to send, what it has to tell basically the producer is, where do I find Kafka? Right. So typically Kafka is on like port 9092. Here it's on localhost. It's called a bootstrap server because generally you're talking to a Kafka cluster. That cluster will consist of multiple brokers or nodes if you prefer. Right. So you need to pick one of them and say, go and talk to this one. It will then get loads of metadata back. The SDK will handle all that for you and better set up a producer. Okay. So the producer has a type. You can see here it says string. That is the key and the value. There's a wide range of options you can choose here. Right? Generally, it's a primitive type basically for the key, and then it can be a more complex type, even your own class for basically the actual value type that you want to send. Interesting enough, Brighter under the hood, which I work on, we actually use a byte array, so it can be generic and ship anything you want. But you can, if you like, if you're writing your own code, choose to use our actual class type. But we'll see that at the end with the schema generation. So having built a producer, saying the key and value is string, I can then send a message, right, a record. And this message is basically sent to a topic. You can see the string there. That's the name of basically where we're effectively going to append our record. And you can see here it's the same generic type, string, and we set a key and we set a value out of our transmogrification settings. Okay. And at the end, we want to flush. So the producer that Confluent gives you is essentially asynchronous. And it doesn't say async, and I know it hasn't got a weight on it, so you might be a bit confused. So what happens is, when I call produce, it's placed on an internal buffer. And a thread reads from that buffer and writes records to Kafka. So the flush statement's important because it says, you might still have items in the buffer. Please can you essentially flush all those out before I shut down? Now that flush method will actually return an integer to you, so you can actually spin in a loop until it gets to 0 and make sure everything is flushed. I'm not doing that in this case because I'm only going to be sending one item at a time. Right? And at the end, like all resources, we dispose of our producer. Right? What about consuming a message? So a little bit of a dot in the code here, just so I can break it up to cert to you easily. But you can see, similarly, we have a consumer builder that basically we're going to write to consume from a topic. So there's a topic here. There's basically, again, the bootstrap servers. Where is Kafka? We also have our group ID. Remember, we are a consumer, so we want to live in a consumer group. Right? So we're just going to pass it an ID and say that is our group. So all it is, it's a string, right? When you're working with Kafka, one of the things is if I want to reset and start reading again, there are various tools that let you do that. Most is just basically add 3 or 4 or 5 to our group number and reset everything. We cheat, right? Because we're lazy and calling the command line scripts to reset the topic count is a pain. We create a consumer. Again, it's a consumer builder. Pass it the config. Again, it's a matching type of string, right? So they need to be matching on both sides because I'm saying what I expect to get off that Kafka topic as a string key and a string value. Okay. Then in our method, what we're going to do is we want it to be a bit generic. We're going to run a run method for the consumer, and it's going to say, I need to have a way of transforming the message, reading this string content and doing something useful with it I understand, and I want to have an action that I perform, a handler, right? What's that going to look like? All right, so in a big try loop, we're going to say subscribe to the topic, right? And then we're going to say consumer result. So Kafka, the Confluent library under the hood, will buffer reads for you, but we just want to get one at a time in a loop. We're going to do a big while loop, which is going to go spin around until we decide to effectively cancel. So that cancellation token will help us cancel our way out of that while loop. We'll throw an exception, basically. So if we EOF, what we're saying is, have we reached the point where the appending is happening? We've run out of records to read. If we haven't, then essentially we can do the translation. We can say run the translator function and then the handler function. If we have run out of things to read, we'll just delay and keep spinning for a while. And again, we close the consumer at the end. All right, topic, pump in an endless loop, read next result, translate the message, handle the message, tidy up when we're done. All right, overall, those two bits slot together, so it's a bit harder to read, but you just seen the code. That try loop is part of the big dispatch method, all right? And to use our consumer effectively, as I say, we're going to pass in our config, essentially, and our topic, right? But the main bit of code you want to see is this. So we create an instance of our message pump, and essentially we pass in a method that's going to effectively translate it into a type. Well, we know our message, when we've written it, we put the key, which effectively is the name of the kind of transformation we're performing, and then the settings, what transformation we want, basically into our class. And effectively, our handler method will get past that particular object, the transmogrification, and we'll spit some stuff out to the command line. We're using spectre.console, which is a nice little command line library if you've not already seen it. This talk is not about spectre.console, but it makes pretty output. All right, that's all that code can I run together. All right, let's do a demo of that so you can see it actually happening. All right, which way is everything? Right, just so you can see, make sure you believe there are no things up my sleeve. I will increase the size in a second. Here is the producer and the dispatcher. That big enough at the back? Cool. Yeah, there is effectively our code saying build the producer, do the producer the message. And here is our code over here, which essentially says, here is our message pump, right? Run it, subscribe, consume. There are various, that's our program code saying, hey, create a message pump and then basically translate it and then actually go in and basically do some work with it, right? All this stuff, you can go look at the code later, is all just spectre.console stuff to make it look pretty. Here we go. Let's try and find demo 2 rather than that one. All right. So just to show you this async partially, we'll just run the producer. So I will be Calvin. And Calvin wants to be an eel. Right? And it's saying Calvin basically enter the transmogrifier and it'll come out as an eel. We have, this is basically the UI for Apache Kafka. You can see it's telling me I've got a broker with only one node because I'm running it in Docker Compose in the background. And you can see effectively I have this transmogrification. I've got 9 messages because I needed to check the demo outside afterwards. And I worried that if I reset everything to 0, I'd doom my own demo. So imagine the count starts from 9 up, right? Interesting enough, you'll be able to see that we will start consuming from that offset, right? You can see messages on the wire, right? So my previous ones were Ian. This one's going to be Calvin. And it's saying Calvin wants to be transformed into an eel. The ones I did for my test, so you can see the test ones are not me. And it's saying effectively, oh, I've got a consumer, but yeah, cool. All right. So what we'll do then is we will consume that. So you can see it's an asynchronous conversation because I'm taking my own sweet time about actually running the next bit. So in other words, It's just sitting happily in that log. And I will say, begin my transformation. Right, and Calvin has been transformed successfully into an eel. Go, Calvin. Okay. That is the basics of sending and producing a message. What does Kafka look like under the hood then? So essentially, you tend to deploy Kafka in a cluster with a number of nodes because one of anything is bad and we don't want it to fail and lose everything. Typically, it's an odd number, and we'll come back to that. The reason is that why, but like 3, 5. And what happens is your partition for a given topic, it writes to one of the nodes, which is the leader, and then from the leader, it is copied to the other nodes in the cluster. So if I lose one of my nodes, hopefully one of my follower nodes will have all of the work that I needed to write. Okay. So we only ever write to the leader. Before about Kafka 2.3, you only ever read from the leader as well. The followers are just there to let you essentially have a resilience in the event of failure. But from 2.3 on, we can read from followers. One of these servers is the Bootstrap server, which is effectively where I read metadata from. We saw that earlier. So I connect to one of the servers, and what my underlying SDK code you don't have to deal with says is which one of these servers is the leader on when I want to do a write, or which servers can I read from when I want to do a read. Right? And that information comes back from Kafka. So it will tell that, but you don't have to see it or deal with it. It's happening under the hood. So who decides which node in our cluster, which broker effectively has the leader? So one of our brokers in a cluster is called a controller. And the controller's job is to say, oh, I've got a new topic, you're going to be the leader. Oh, the leader crashed, you're going to be the leader. And it chooses to decide who is the leader, right? So who elects one particular node in your cluster as being the leader? So this kind of problem is why Zookeeper appears quite often in Kafka. So you may or may not be aware, quite often Kafka clusters also have a Zookeeper cluster, which makes life a little more complicated. So Zookeeper effectively provides distributed kind of primitives, including locks. And so what happens is when your Kafka cluster starts up, the individual brokers in the cluster try and essentially write an ephemeral Z node in Zookeeper. What the hell does that mean? What it means effectively is they say, okay, so the way that the nodes work in Zookeeper is a bit like a file system directory with slashes in between. One of them says, I want to be root. So that thing basically says, everyone says, I want to be root. And it's called an ephemeral node because one of your wins becomes root as long as you are connected. If you disconnect from the Zookeeper cluster, the assumption being you've crashed or gone down, then essentially the ephemeral node you created disappears. One of the others that's constantly trying to create the ephemeral node wins, and now it's got the root, and therefore it becomes the controller of the cluster. So essentially, the way we do leader election is to effectively win at creating the root node in a Zookeeper ensemble. That's all a little complicated. So from about version 3.3, I think, Kafka basically now runs without Zookeeper. And to do that, essentially, it has an implementation of the consensus algorithm called Raft, Kafka Raft, or Craft for short. Software engineers, aren't we great? And Craft lets it basically, the brokers in the cluster decide amongst themselves who is going to be essentially the controller. Now, or effectively the leader. Now, what happens is you can declare for any one of your nodes in the cluster what kind of roles it can fulfill. It can be a controller, which means it can essentially participate in the selection to be the thing that becomes the leader and decides what partitions get allocated and where. It can be a broker, which means it stores data, or it can do both. And the advantages are mainly around performance, particularly in larger clusters. So when a producer writes, it has to decide how long is it going to wait for Kafka to do the work of replicating from the leader partition to the followers. Now, I can choose to be very fast by setting ax equals 0. And that means I'm not even going to guarantee to you that it actually successfully wrote to the leader. I got the message, maybe I'll succeed at writing to the leader. Ax equals 0 says, or its acknowledgements equals 0 says, I don't really care about safety, I just care about speed, right? Foot on the floor, black windows, let's go for it. Right? Generally, it means you'll get message loss, but that may be okay, right? So we do things like track couriers, where we can afford to lose some messages, right? Ax equals 1 says, only write it to the leader. You're going to propagate it for me. I'm not going to wait for that. It's a lot better, because at least I know it's written to one of the nodes in the cluster. And my expectation is, hey, probably the others will get it. So it's pretty fast. The danger is my leader crashes and a follower gets selected as the leader and it hasn't yet received all of the updates from the leader. So it's behind, which results in what we call message loss. You won't now have those records that went missing in the time in between. It's a compromise between speed and safety. Ax equals all is what you do if you can't accept message loss, right? The producer says, I'm going to write to the leader and I'm going to wait till it's been copied to all of the nodes in the cluster, and then I will treat it as acknowledged. Sometimes a broker stops being able to be reached in a decent enough time frame. The way that Kafka measures this is says, how long did it take you to catch up with the leader? If that gets too slow, it may just be it stopped, right? But if it gets too slow or it just stopped, it becomes what we call an out-of-sync replica. Kafka says, that one's broken. When we do producer equals all, we won't include that one. And no one should read from it either. I'll alert basically, an operator, someone needs to fix that particular node in the cluster and bring it back online and let it catch up. All right. So how do we take advantage of this information when we are writing our producers in C#? Okay. So the first thing is when we configure Kafka, so that producer.config that we only had bootstrap in, you can see in that little box in the middle, there's some other things we can write. So we can tell it the number of ax. So here you can see we're saying ax equal to all to be safe. We can also, don't forget that basically Kafka is going to use a buffer with a little with a thread reading from that buffer to actually write for us. We can say, hey, in the event that essentially you ask for ax equals all, but the response you get back says we didn't write that, or you don't get a response at all, retry. So it will retry under the hood for you. You can tell it how many times to retry, and you can tell it how to back off between retries. So what kind of gap are you going to give to prevent overwhelming the server? You can also tell it how many in-flight requests can I have. Now, in-flight requests are how many threads can be reading that buffer at one time. If you set it to anything other than 1, you will risk losing the sequence because things may get written from the buffer out of order. So if you require ordering, you set that to 1. There's a workaround for that, but I'm going to tell you that in a second. All right? So this code here reliably produces a message in C#. You can see a couple of things that I'm doing here. The first is essentially I'm setting up some error handling and some log handling so I can kind of be informed. But the next thing I'm doing is setting the producer.config with some more elements. So I'm saying, I actually should say ax equals all, but you can actually worth you seeing ax equals leader there, right? So I can tell it the number of ax I want. Ax equals leader is this ax equals 1. Ax equals all would be truly safe. Message send max retries, saying I want to retry 3 times. So I'm saying I only have 1 in flight, right? You'll see enable item potencies commented out there. We'll come back to that in a second. If turn on enable delivery reports equals true. So remember I told you that produces async, right, from a buffer. So how do we know if we just call produce and our code moves on, whether we successfully sent something to Kafka? So delivery reports will tell us. And we'll see how that works in just a second. Okay. So you can see here what we're going to do when we produce, we're going to pass a handler in that third parameter for our delivery report. And you can see that's up above, the action delivery report. So it's a callback where we will say, we will basically receive the response from you telling us whether or not you wrote that record. What are you going to do with that, right? So we're going to fake what you probably need to do a little bit. But here we've got a kind of fake in-memory outbox, generally need a persistent one, right? I need a sweeper for it. Where we're going to say, okay, when we receive the delivery report, we'll mark the status of this item as sent. What we do a bit further down on line 19 is we say, when we have a message, we'll put it in the outbox. The outbox says, this is something we've intended to send. And we'll only mark it as sent when the delivery report comes back from Kafka saying, hey, this was done. Typically, in frameworks that support outboxes, a background worker thread then basically spins saying, hey, are there any messages that were inserted in quite a while ago and I haven't seen a delivery report for, then I will resend it. All right. But you're going to have to figure out, what am I going to do on the failure to send a delivery report? And some kind of outbox is typically the strategy you will end up using. All right. And this is reliably producing a message. That's just basically a summation of all that code. So you can see it's all in one big blob. All right. There is an async version of produce. It's basically produce async, and you can await it. So rather than writing effectively a callback, you can essentially say, okay, just give me the report as effectively the return value from calling await produce async. You might think to yourself, this is going to be better because I don't have to write callbacks. I'm using async await. That's all good. It is slower than the other method, right? Because what happens is you create all this async await infrastructure around something that was asynchronous anyway and was actually working just by a separate thread. So generally, your throughput will go down if you use an async await approach towards Kafka clients, right? So bearing in mind, because it's a bit counterintuitive, you may end up with here because you end up with some kind of model that says, oh, I need to use async because I'm in an async flow, but I would avoid it. All right, so let's have a look at how that all works. So, close these down so we don't get confused. So last time, just again, to make sure you basically believe that I am showing you real things. All right. This is the message pump again that we saw earlier, right? And in here, effectively, you should see that's storing offsets in the consume. We don't want to see that yet. That's the next bit of the demo. Where am I? Dispatcher. There we go. Right, you can see we've got the outbox. We're marking the status in the event when something comes back. All right, we're saying when it happened. What happens is we create the message, add it to the outbox, produce the message, handler gets called when it's done its report. We mark the status there and show basically it happening. All right. The outbox in this demo is just in memory. That's not a real outbox. Please don't build your production systems on Ian's in-memory outbox in his demo code. Go and use Brighter if you need to understand how to use outboxes. An async dispatcher is just there for reference for you, which shows you how that one works instead, but we're not actually running that one, we're running the normal dispatcher, right? Okay. And what we'll do, I think, if I can find the demo 3. I think you'll get a little hint of what the next one does as well. Spoilers in the consumer, but there you go. So Calvin, and I want to be transformed into a tiger, right? So Calvin has been sent. Right, do you see now what we get below is a little box which effectively is looking at the contents of the outbox and is saying to us, yeah, that message for Calvin was sent. This is when it was sent, etc. In terms of timing, right? And we should see that if we grab that out, we'll see Calvin being transformed into a tiger. All right. We can use something called transactional reliability in Kafka. Don't worry too much if you don't grasp this section. You don't need it so much. So with transactional reliability, we say, I want to make sure that when you do these retries and this underlying buffer async operation, you're actually only going to send this thing to once, right? And so effectively, you can create a transaction that says, please only send this once. What you do is that allows you to set maximum in-flight request per connection higher because it was serialized stuff. And effectively, you can set enable item potence then to say once only. You also have to set a transaction ID, which says, who am I for the point of uniqueness of transactions. And what you do, you can see here effectively, you need to do ax all, and that automatically sets item potence basically rather sets ax all, max in flight to 5, and max int retry. So max int retries basically means retry forever, right? And it adds up to 5 at once. And what you'll see is we do a begin transaction, a commit transaction, or an abort transaction. Typically, there's this very specific scenario where you want to use this, and that is essentially when you are reading a stream and writing to another stream. So you're reading off one topic and writing to another topic, and what you don't want to do is signal that you have essentially read from the first topic until you've written to the second topic. That is mainly why transactions are required, right? So if you have that scenario, where you're putting one or the other, and you want to make sure, effectively, for every record you read, there's a matching one on the output, you may want to use transactions to help you do that. Okay. Now, what it's actually doing in terms of basically saying read and the output is it's basically making sure that you don't increment the offset on the consumer until essentially you have, or rather, you don't say it's read from the producer until you've incremented the offset on the consumer to say it's written. So offsets. Before, we didn't see any code managing offsets. We're just reading from the consumer, and we're assuming effectively that it was incrementing the offset. And that is true, right? So what happens here in this code is we are effectively auto-committing and auto-storing offsets. Now, we don't have to set this as we're doing here. That is the default. It has to be explicit. That's what we're doing here. So what does that mean? Okay. So the offset commit, when it's auto, says, as soon as I read something from the stream, treat that as read and commit that offset. Okay. Auto offset store equal, auto offset trues, auto offset store rather, says, as soon as I've read it off, store the offset value to say, essentially, I've read that one. And auto offset commit rather says, every 5 seconds, go to the offset store, which it provides for you in memory, and write any commits to the Kafka server. Okay. And that is the out-of-the-box behavior. Okay. The problem with that is this, right? If in this code, at the point where I consume, I am storing the offset, which is then in the background going to get written. If I fail in the translator or handler step, that offset's already been written and I can't retry that work. Or more particularly if I crash, right? But after I've read, but before I essentially have done the work that I intended to do. So I don't really want to commit an offset until I've done the work that I want to do as a result of reading, right? I want to transmogrify Calvin before I manage the offset, right? So what do I do to do that? So actually the easiest option in C#, and it does vary by library. So C# is one of a class of libraries along with Go, Python, built on a thing called libra-d Kafka. So it gets most of its options from that. Is to essentially say, manually store the offsets, but auto-commit. What does that mean? It means that I will store the offset by triggering by calling store offset when the work is done. So you can see here in this while loop, what I'm doing is saying read from Kafka. If I have translate it and handle it, if I've successfully translated and handled it, then store that offset. I've got enable auto commit, so in the background, every 5 seconds, Kafka will be effectively committing my work to the topic consumer offsets. Now you may decide 5 seconds is too high a risk, right? But if I crash before I've written that, I'll get the work again, and you can play with that particular interval. Okay, that's the default that you get out of the box. The other alternative is to say, yeah, I just want to commit when I am done. I don't want to basically store and then commit in the background. So essentially, I'll turn both auto commit and auto offset store to false. And I will just commit manually when the work is done. This is more chatty, right? So I'm making more calls to the server so it can have a performance impact. So your trade-off is the speed of the consumer versus the risk of some message loss. Because I've taken control of how we basically get those offsets into Kafka, either I'm writing them to the store, letting it commit in the background, or I'm committing manually, I now have to basically also tell Kafka what to do. If I, as a consumer, lose a given partition because it's been allocated to somebody else. So maybe I had 2 partitions, we were in very quiet period, we ramp up to peak load, suddenly there's a whole load more consumers, one per partition, 2 or 3 partitions get taken away from me. I have to essentially make sure everybody else knows how far I got. So I either have to essentially store the offset or commit the offset, depending on whatever my strategy was that I was using within my handler. So when I create my consumer, I've got to make sure that's matching, right? All right, so let's do a quick demo of that. I think I can do it from demo 4. Let's just see. There are a few extra demos. It's for time that they don't all get done. They are in there. You can go and have a look at them yourselves later and go, oh, that's an exciting little change. So this one here, you can see just that while loop. We're going to basically store the offset. And then what we're going to do is basically to the console, we'll just write out the information that we stored the offset, right? And then essentially in the background, Kafka will commit that. It's a little bit hard to show you all of how it works, but hopefully you'll get the impression from this. So we're just going to produce a new message. Calvin, what would you like Calvin to transform into? Again? A baboon, yeah. The one I struggle to type right every time because I can't spell baboon. Someone had to pick baboon. All right, Calvin's going to turn into baboon. All right, so we've sent that message. And begin transformation of Calvin into baboon, right? Calvin is now baboon. You can see we stored the offset, partition 0, offset 10, right? You can go and look at the consumer offsets topic. It wouldn't be meaningful. We'd look at the UI together and be scrolling through, and nothing would actually happen of any value for any of us. But if you want to go and check stuff, you can, right? Just let you know that that is a viable thing to do. Okay. All right. I don't have time. 9 minutes. All right, we should manage that. Resetting the offset. So as I mentioned, sometimes you may find, particularly if you're developing locally and you're playing around with stuff, going, oh, I've got all these offsets. My consumer's now at offset 94 or whatever, and I want to start again and replay everything and fix my bugs, etc. Or even sometimes in production scenarios we get it. So the trick is just essentially rename your group ID. There are tools which you can get in the Kafka bin library, which you pass in and you say, hey, for this particular partition and this group ID, reset all the offsets to 0. And that can work locally, but if effectively you've got a production system managed by another team, et cetera, you have to issue a JIRA ticket request to get them to do that. Sometimes just increment the number of your group. Honestly, makes it a lot easier. All right. Serializers, deserializers, and the schema registry. Okay. So notice we haven't actually used the schema registry up to now. So it's not compulsory in Kafka, but the Kafka ecosystem, things like Connect, KSQL, tools that we haven't got a lot of time to get into, but effectively help you essentially do data engineering pipelines, tend to depend on schema. Plus, schema is actually quite useful to make sure that you are obeying the rules when you send about the schema that effectively you've defined lives on that topic, right? It's a bit less useful when you consume. It's Postle's law. We should be tolerant when we consume, but strict when we send. So we want to kind of say, hey, does the message we're sending match the schema? You can also get a schema registry to tell you, will I break anybody? So the rules of backwards and forwards compatibility. So how does it work? So Kafka can choose to serialize, not just as a string, your key and your value via Avro, JSON schema, or protobuf. JSON schema effectively is obviously one most of us know, the kind of JSON thing. Avro can actually be based a JSON or binary, it's just a different schema format. And protobuf is effectively the Google format. I haven't got time today to get into the depths of what those individual schemas, how they look like. So you have to do research depending on what you want. Avro is essentially the sort of native Kafka one, and some tools work better with Avro than work with JSON schema. So what I want to do is define a schema for my message, right? I want a schema for transmogrifications. And then effectively I set the schema that I want for a given topic. Now there's some complexity here. Normally I would recommend having a single schema for a given topic. Some folks like to send different types of message on their Kafka schema because they want to have what we call domain events that are much more granular, ordered in sequence. They have to have multi-topic schemas, and that gets a bit harder, right? There's a relationship called the subject, which basically determines by the schema registry what topics is it, or what schemas it got for a topic. This hideous table, don't worry about reading it. You can look at it on the slides if you're really worried. Tells you about compatibility between various changes you might want to make, the order in which you want to start consumers and producers depending on the changes that you're making. You can pretty much summarize this, right? So effectively, if you want backwards compatibility, it says consumers using the new version can read messages with the last version. In other words, my consumer is now on version 14, but I can read messages that come in version 13. Transitive, which is the little option below, just says actually 13 all the way down. I can read any message that's sent in the past. Forward says a producer using the new version can send a message to a consumer who has the last version. So I can send a message that has version 14, but consumers that only understand version 13 will still work. And transitive means consumers with all the versions all the way down, right? And full basically means producers and consumers effectively may be on the one prior version. So if 14 is current, either could be on 13, either the producer or the consumer, we can still communicate. And transitive basically means producers and consumers aren't breaking each other at all. Right? And you need to figure out what you need to set, and essentially a little bit it determines the order of upgrades, etc. So how does a schema registry work? So the schema registry works, my producer, when effectively I'm producing a message, so I've registered a schema in my schema registry. If not, it will actually register one for me usually. Writes basically it says to the schema registry, hey, I'm going to write a message. If you've got a schema in there, it will check against it. It will then effectively apply the schema ID. Well, you need to apply your schema ID to your Kafka message. We'll come back to that in a second. The consumer can, if it wishes, then read the schema as well from the schema registry and check the message. Generally, we tend to check on the outgoing on the producer. So the producer says, I'm going to send a message, look in the registry, get the schema, compare it against the schema, ask what rules you've got, forwards, backwards, or full. Does it obey those rules? If so, send it. Consumer can check and say, hey, does it match the schema? Should I process it? But we don't tend to. The nasty bit is that Kafka didn't support headers until, I don't know, version 0.11 or something. And part of the problem with that is, how do you then know what the schema ID of the message is? So because it needed to do this quite early on, Kafka decided I'll mangle the value. So I'll basically insert 5 magic bytes at the beginning of the value. The 0th byte is essentially which version of Confluent schema registry magic bytes am I on? It's pretty much been version 0 since eternity. And the next 4 bytes are the schema ID. So the identifier for the schema in the registry. This tends to mean you need to use Confluent's SerDes family of serializers to actually do the serialization. The only slight pain in the ass of that is that the JSON one is still on Newtonsoft JSON with NJSON schema, and it's an older version of NJSON schema, and you end up marking up your code for Newtonsoft JSON with NJSON schema as well as system.text JSON, right? So it's a little bit behind on the Confluent library. What you do is essentially when I'm producing with the schema registry, I effectively need to get hold of a schema registry. It's effectively runs as part of your cluster normally. So here we're just creating a reference to the schema registry. We're caching it so that effectively we don't have to repeatedly ask for schemas. We'll store them locally on our actual app so that it will look up locally first for stored ones that only make the call to the actual external schema registry if it needs to. The advantage of that is the schema registry is down. More than likely, your app has already got the schemas locally it can check against. It doesn't have to keep calling back to the actual schema registry. And then we have to use the Confluent SerDes serializer to do the work. All right. In the interest of being on time, I won't show you all the code that does that because you just saw it. You have to trust me that it really exists. And we will do the demo instead. Okay. Let's clear that. And clear this. So transmogrification. I'll be Calvin, just so we can distinguish them. The transformation, I'm going to be a bug because it's short to type. And can you see around the very bottom, we'll do yes, that makes sense. There is now basically, what I'm outputting is there is a schema that the schema registry has created to support that particular message. So effectively, it's the transmogrification setting schema. Type object is essentially its JSON schema, and it's effectively got properties of name, in other words, who's being transformed and the actual transformation. And effectively, if I tried to send something that didn't match that schema, if I changed essentially from saying name to identifier, it would break and say, that's not a compatible change here. All right? Cool. All right, and we're almost at the end. Okay, just some links. So again, we saw this at the beginning. All this sample code. There are a few demos we didn't actually get to. You may find helpful. this presentation, I will upload a proper PDF version of this one, or provided I can get the PDF into GitHub. There's an earlier version. It's similar content. And Brighter, if you want to come and look at us, we do support things like Kafka natively out of the box. And we preserve ordering for you. So we have a single-threaded reactor model, which may mean nothing to you, but effectively means we preserve the ordering of the stream. Other topics, Kafka Connect and KSQL. So Kafka lives in an ecosystem of tooling. Kafka Connect lets you read things out of databases or other messaging systems and effectively import them into a Kafka stream, and then essentially also write things from a Kafka stream to either a database or another messaging platform. Connect, you have to run as a cluster. It's all Java, effectively, but you just need to run the cluster. It's okay. We find that the adapters are not great. We actually prefer on the bottom, there are two alternatives there to connect. Flink, so I know that Confluent have gone quite big on Flink recently. They brought up a Flink consultancy. Flink is a data engineering tool, which is probably better than Kafka Connect. They're doing this. We really like a little Go tool called Benthos. Benthos.dev is basically the website, which effectively does for us what Connect was supposed to do, which is it's a data engineering tool pipeline that connects databases and streams. All right. And there are streams applications. It's more common in Java. There's a .NET port, and that essentially is mainly used when you are moving between one stream or another, doing some transformation processing in between. And that, ladies and gentlemen, is that. Thank you very much. I hope that was helpful and you now know how Kafka can be used by .NET developers. If so, a green ticket in the box. Thank you very much. You can ask me questions while I'm packing up if you've got anything you need to ask. So.